Today's presentation is on solving gas law problems. We're going to be looking at solving Boyle's law and Charles' law problems, which were derived in the previous video. The first example, we have a sample of helium gas that occupies 521 milliliters at this pressure, 1,752 torr. We're going to assume that the temperature is held constant and then determine the volume of the helium at a new pressure, 752 torr. When we have a problem like this, these are called corrections. And what that means is that we have a volume here at a certain pressure. We change the pressure and we're going to correct to a new volume. In this case, we're assuming that temperature is held constant. So we can eliminate temperature from consideration in the problem because it doesn't change. So if it doesn't change, it would have no effect. So as we're solving the problem, the first thing that we want to do is try to sort out the meaningful numbers that are in the problem. It does not matter that the gas is helium. Any gas is going to respond in the same way. We do have a volume, so we can label that V equals 521 milliliters, and P equals 1,752 torr. We're going to have the helium move to another pressure, so here's our second pressure, 752 torr. And we want to know what is the new volume. And our equation for this that relates pressure and volume is Boyle's law. And our equation for that is P1V1 equals P2V2. In the situation like this, we have two values. This volume is known at this pressure. The ones that go together, we know both of them, are our first conditions, and then the one that we're missing is the second condition. This pressure goes with the new volume, so that's also a second pressure. So then, once we have everything labeled, all we have to do is plug in the values. First pressure is 1,752 torr. Corresponds to a volume of 521 milliliters. That equals the new pressure, 752 torr, so we have a drop of 1,000 torr. And we're going to solve for the value V2. To do that, we're going to divide by 752 torr. That cancels. Torr cancels. And when we do our math, 1752 multiplied by 521 divided by 752, that comes to a new pressure of 1,195.1 milliliters equals the new volume. We can then adjust that to the proper number of significant digits. It looks like 3 significant digits. So we would say 1.20 times 10 to the third to get it to 3 significant digits. And that again would be milliliters. So either of those would be an acceptable answer for me at this point, I think. Next problem. Again, we have some information given to us about, in this case, some argon gas. Again, it doesn't matter what gas it is. So we've got a volume of 300 milliliters of argon at a pressure, this time in kilopascals, 99.4 kPa. And we've got a temperature given to us. Temperature equals 20 degrees Celsius. If the pressure is increased to standard pressure in kilopascals is 101.3 kPa. That was given in a previous video. Temperature remains constant, and we want to know what is the final volume. Okay, we can see here that temperature is 20 in both conditions, so that can be eliminated. That was information that we did not need. We have our equation, P1 times V1 equals P2 times V2. Our initial pressure is here, our final pressure here, final volume there. Okay, so 99.4 kPa times 300 milliliters equals 101.3 kPa multiplied by V2. And let me divide 101.3 kilopascals, 101.3 kilopascals. V2 is then equal to 294.4 milliliters. And checking to make sure the problems make sense. Remember, pressure is inversely proportional to volume. So if pressure goes up, volume should go down. That's what happened here. Pressure went from 99.4 to 101.3. That's an increase in pressure, so volume should decrease. And it did, slightly. Slight increase in pressure, slight decrease in volume. All right, our next problem. We've got a gas at temperature, T, 99.8 degrees Celsius, at a volume of 154 milliliters. What will be the volume at a temperature of 10 degrees Celsius, assuming no change in pressure, meaning that we can leave pressure out? This is Charles' law, which is V over T equals V over T. Initial conditions, final conditions. V1 over T1, V2 over T2. 1, 2. Now, according to Charles' law, volume is directly proportional to Kelvin temperature. So we're going to have to convert these to Kelvin by adding 273 to each. This is 372.8 Kelvin, and this is 283 Kelvin. Then we plug and solve. Volume 1, 154 milliliters, over T1, 372.8 Kelvin, and V2 is what we're solving for. V2 over 283 Kelvin. V2 is then going to be equal to 154 milliliters times 283 Kelvin, because we're cross multiplying, and then divide that by 372.8 Kelvin. Kelvins cancel, and our new volume is 116.9 mLs to 3 sig figs, 117 milliliters. Don't forget to convert to Kelvin. It's an important step. And next problem, we've got volume, 567 mLs, temperature, 305 degrees Celsius, pressure, 1.02 atmospheres. It's cooled at constant pressure, so during the cooling, that stays the same, so we can eliminate it. We want to know it's cooled at constant pressure until its volume becomes 425 milliliters. What will the new temperature be? Okay, so One thing that we're going to have to do before we solve the problem is anytime we have a temperature, go ahead and convert to Kelvin. The temperature here plus 273 equals 578 Kelvin. We then have the equation V1 over T1 equals V2 over T2. Identify the conditions that go together. This volume occurs at this temperature. This volume will occur at this temperature. So plug in. We've got 567 milliliters over 578 Kelvin equals 425 over T2. This gives 567 milliliters times T2 equals 578 Kelvin times 425 Kelvin. Cross multiplying. We then divide by 567 milliliters. And T2 is then equal to, in Kelvin, because milliliters will cancel. I'm sorry, this is supposed to be 78. This is supposed to be milliliters. I had a unit issue there. Milliliters cancels. I'm left with Kelvin. So T2 is then equal to 433 Kelvin. If we wanted that in Celsius, so this is actually one answer, that would be an acceptable answer. Minus 273 to get to Celsius is 160 degrees Celsius. Either one of those would be acceptable answers. Okay, those are your examples of Boyle's law and Charles' law, and that ends the video.